Welcome to the Explainer! So glad you're here. Look, if you're the kind of focused learner who loves getting right down to the actual nuts and bolts of how things work, well, you've landed in the absolute right place. Today, we're tearing into the really high-stakes world of low-voltage assembly safety. We're going to break down the critical concepts of busbar blueprinting, specifically clearance, creepage, and the rigorous math that keeps our electrical infrastructure from literally going up in smoke. We're taking these dense technical manuals and transforming them into a crystal-clear step-by-step masterclass. So get ready to look at your electrical designs in a completely different light.
Okay, real quick, here's our roadmap for today. We'll start with the hidden cost of spacing, then pit clearance against creepage. After that, we'll decode the IEC standards, tackle the pollution and altitude problem, and finally, tie it all together with designing for reality. Let's jump in.
Starting us off, Section 1, the hidden cost of spacing.
Okay, let's dive into this. I really want to emphasize right off the bat that busbar spacing is definitely not some minor cosmetic detail you just, handle at the very end of your build. The source material makes this incredibly clear. Undersized spacing is a direct path to arc ignition, severe insulation tracking, and dielectric failure. Basically, treating it as an afterthought is a recipe for a catastrophic meltdown and entirely avoidable downtime on the factory floor. It's a huge deal.
So think about your own engineering workflow for a second. Why do we still treat spacing as a late-stage check? Honestly, it's a fundamental flaw in how a lot of panels are built. In the real world, electrical clearance and creepage distance absolutely must be set way before you freeze your copper routing or your enclosure designs. If you try to shoehorn these safety parameters in after the physical geometry is locked, oh man, you are setting yourself up for a really bad time.
Which brings us right to Section 2, clearance versus creepage.
All right, we need to establish the core mechanics of how electricity actually tries to escape its intended path. It's basically two distinct avenues of attack. On the left, we've got clearance, which physically fights its way straight through the air. And on the right is creepage, which sort of crawls along the surface of your insulating materials. They occupy completely different physical spaces in your assembly. And here's the absolutely crucial takeaway. Passing one of these checks does not mean you automatically pass the other. You can have picture-perfect clearance and still fail catastrophically on creepage.
Let's define them properly, starting with clearance. Clearance is the absolute shortest distance through the air between two conductive parts. Its one and only job is to prevent a flashover through the air during a sudden overvoltage event, like a lightning strike or a massive transient spike. Because it's an air gap, it's driven heavily by the rated impulse withstand voltage, or Uimp. And interestingly enough, it's also driven by altitude, which we'll get into a bit later. Essentially, it controls dielectric breakdown right through the air.
Now, on the flip side, we have creepage distance. This is the shortest path along an insulating surface between conductive parts. So instead of sudden transient spikes, creepage is all about the steady working voltage over time. It's governed by that voltage, plus the pollution degree of the environment and the actual material group of the insulator itself. Creepage is what limits surface tracking, long-term carbonization, and leakage current across the insulation, especially, and I can't stress this enough, when it's exposed to humidity or contamination.
Moving right along to Section 3, decoding the IEC standards.
Now we've got to tackle the bureaucratic side of the design. Look, I know reading standards isn't exactly a weekend hobby, but we're going to de-jargon these documents right now because panel builders mix them up all the time. Over on the left is IEC 6664-1. This is the underlying insulation coordination standard. It gives you the actual math, the dimensioning logic, the altitude guidance. On the right, we have IEC 61439. This one governs the low-voltage switchgear as a finished product, detailing the construction rules and requiring routine verification. Basically, think of 6641-1 as the textbook that teaches you the math and 61439 as the final exam verifying your assembly actually passes. Oh, and a quick note from the sources. A standard insulation Megger test, that is not an acceptable substitute for clearance verification under 61439. You need dedicated power frequency or impulse-based methods for that.
Now, what's really fascinating here is how these numbers scale. Just look at these baseline values for a pollution degree 3 environment. Down at 250 volts, your clearance is 3 millimeters and your creepage is just slightly higher at 4. But scan down that table to 1,000 volts. Clearance requires an 11 millimeter gap, but creepage? It demands a massive 22 millimeter surface path. It literally doubles the clearance requirement. Creepage scales so much faster as voltage goes up. This proves exactly why you can't just set an air gap and assume your surface path is totally fine.
Let's shift our focus over to Section 4, the pollution and altitude problem.
So let's talk about the real-world environmental variables that explain why a flawless paper design often falls apart on an actual factory floor. Pollution degree is definitely one of the most misapplied variables out there. PD1 is basically a perfectly clean, sealed environment. Pretty rare. PD2 covers ordinary non-conductive pollution with occasional condensation. But PD3, that covers conductive pollution, or dry contamination that actually becomes conductive the second condensation hits it. Here is a massive warning for designers. Classifying an industrial switchboard as PD2 when it actually lives in a PD3 environment is a really common and a really expensive mistake. For industrial settings, PD3 is pretty much always your defensible starting point.
Next up, we've got the Comparative Tracking Index, or CTI. This explains why the exact same voltage can require completely different creepage paths depending on the insulator you use. A higher CTI number basically means the material has way better resistance to electrical tracking. Group I materials like your ceramics and thermosets are incredibly resistant. What that means is if you use a high-quality Group I material, you can mathematically justify shorter creepage paths than if you went with a weaker organic Group 3 surface, even under the exact same electrical stress. So yeah, picking good materials literally saves you space.
And then there's altitude. I absolutely love this fact because it always catches people off guard. High altitude physically weakens air insulation. The air is thinner up there, so it's just less effective at stopping an arc. The IEC standard gives you normal values up to 2,000 meters. But check out these correction factors. If you're installing a panel at, say, 5,000 meters above sea level, you have to multiply your clearance gap by 1.48. That means you need an air gap almost 50% wider just to get the exact same level of safety you'd have down at sea level. If you forget to adjust for this, your high-altitude panel is basically a ticking time bomb.
All right, we've reached the final phase, Section 5, Designing for Reality.
Okay, let's put it all together. We're going to combine all these standards, voltages, and real-world variables into a practical logic chain for a standard 1,000-volt distribution panel. Step 1. Fixed distribution equipment like switchboards fall under overvoltage category 3, which maps out to an 8 kilovolt impulse duty. Step 2. That 8 kilovolt impulse directly translates to an 8 millimeter minimum air clearance gap. Step 3. We verify our altitude is under 2,000 meters, so no correction factor is needed here. And Step 4. We hit the licensed IEC tables for our creepage based on a PD3 industrial environment, which spits out a conservative drafting figure of about 22 millimeters. Boom! This is the exact logic chain you use to turn abstract guidelines into physical manufacturing dimensions.
Now, let's tackle a huge misconception head-on. Can insulated bus bars use smaller clearances than bare bus bars? Well, the answer is sometimes yes, but only, and I mean only, when the insulation system actually has validated dielectric capability. You absolutely cannot just slap a piece of shrink wrap sleeve on a bare conductor and decide you're going to ignore the air clearance logic. The difference between bare and insulated isn't just copper with a sleeve versus without. It's about verified dielectric performance across thermal and mechanical aging versus just hoping the air does its job. If your coating ages or cracks, your design instantly reverts back to bare busbar behavior. Finally, our sources really hammer home the importance of practical headroom and mechanical stability. Mechanical stability is inherently linked to electrical safety. Just think about it. A short circuit event generates these massive electromagnetic forces that will physically bend and deflect your conductors. If a short circuit bends your bus bar, your perfectly calculated 8 millimeter clearance, it's gone. It completely vanishes in a millisecond. Like the Copper for Bus Bars guide points out, having greater section stiffness reduces that deflection. You also have to think about everyday realities, like how dust settles way faster on flat horizontal surfaces than on vertical edges, which slowly ruins your creepage path over time. Oh, and last-minute hardware changes on the factory floor? They will always erode your electrical margins.
So, as we wrap things up today, I want to leave you with this provocative thought. Are your current layouts truly resilient, or are you just getting lucky on the test bench? Because as we've seen, reliable switchboards just don't happen by accident. They come from correctly classifying your pollution degrees, actually understanding the math behind the IEC standards, accounting for things like altitude, and locking down your mechanical stability long before a single piece of copper is ever bent. I challenge you to take these insights, seriously rethink your baseline assumptions, and build true insulation coordination into the very beginning of your next design. Thanks so much for learning with me today, and keep exploring.